Hi, this is Dr. Goldstein, and today I'm going to be discussing derivatives of trigonometric functions. So let's begin by discussing the derivative of sine of x. I think the best way to understand the derivative of sine x is to actually look at the graph of sine x and consider what the tangent line looks at different points. So remember, anytime we have a local min or a max on our function, we have a horizontal tangent line. So for example, when x is equal to pi over 2, we have a horizontal tangent line, and what that means is that it has a slope of 0. So if I were to plot this as a function, if I were to plot the slope of this line as a function, its y value is 0. Now you'll notice on the graph of sine, I have a bunch of different places where I have horizontal tangent lines, and so what that means is that there's a bunch of different places on the derivative of sine where I have a y value of 0. So I have a bunch of different roots. And all of these roots occur at odd multiples of pi over 2. Okay, if we look between each of these roots, let's say at x equals 0, it looks like we have a positive slope. As we look at different points between each of these two roots, we see that we have positively sloped lines. Now at minus pi over 2, they start off with a slope of 0. They get steeper and then less steep and then go back to 0. So it looks like at 0 I have a slope of about 1, and so the graph of the derivative might look something like this. And actually I'm going to switch colors so this is a little bit more visible. Graph of the derivative looks like it might be something like this. Now if I look, for example, between pi over 2 and 3 pi over 2, I have negatively sloped tangent lines. As we start to move from pi over 2 to the right, I have tangent lines with a relatively small slope, and then they get steeper. It looks like they're at their steepest around pi, and then they get less steep as we head to 3 pi over 2, and then at 3 pi over 2 we have a slope of 0 again. And so if I were to draw that, it looks like the slope gets as low as minus 1, and so the graph of all of these slopes looks like it might be something like this. And I can keep on doing that. I can keep on graphing the slopes of these tangent lines, and what we end up getting is this curve here. And now maybe you've realized this already, or maybe you'll notice it once I point it out to you, but this purple graph that I've drawn, that is the derivative of sine, well, that is cosine. That is the graph of cosine. So this is an intuitive way of seeing that the derivative of sine is cosine. Now, if you want a more rigorous explanation, I'm sure that you can find a proof somewhere, but this is my favorite way of seeing that the graph of sine is indeed, the derivative of sine is indeed cosine. So let's look at a couple of examples of using this fact. Let's say that I want to take the derivative of 3 times sine x. Well, I know that when I have a constant multiple of a function, its derivative is just a constant multiple of the derivative of that function. So I know that I'm going to have 3 times the derivative of sine x, and what we just said is that the derivative of sine is cosine, and so overall I'm going to get 3 cosine of x. On the other hand, if we consider the derivative of sine of 3x, here I have one function inside of another function. So this function, 3x, here, this is an inside function, g of x, and so I know the derivative of sine of 3x is going to be the derivative of sine, which is cosine, with this inside function, 3x, plugged in, and then times the derivative of that inside function, times 3x, using the chain rule. So the derivative of 3x is just 3, and so overall we have cosine of 3x times 3, and usually when we simplify we'll just write this as 3 times cosine of 3x. So those are two examples of using other derivative rules along with trigonometric functions. Okay, let's look at the derivative of cosine, and we're going to approach this in the same way as we did the derivative of sine. So again, let's start by looking for places where we have horizontal tangent lines, and those occur at 0. And so I know the value of my derivative at 0 will be 0. At pi, I have a horizontal tangent line, and so my derivative is 0. And also at minus pi, I have a horizontal tangent line, and so my derivative is 0. Now, between 0 and pi, all of my tangent lines have a negative slope, and it looks like they get to their most negative around pi over 2. And so if we graph the derivative between 0 and pi, it might look something like this. And then as we move on from pi, I have positively sloped tangent lines. And it looks like they're at their steepest right at 3 pi over 2. And so the graph of the derivative of cosine might look something like this. And if I keep doing that between each of these roots, this is what the derivative is going to look like. Again, just taking the slopes of the tangent lines and translating those into values of a function. Now, this is not y equals sine x. If you remember, y equals sine x starts at 0, but then it increases to 1 before it goes back to 0. So what we have here in purple is the graph of y equals negative sine x. It's the graph of sine x flipped over the x-axis. And again, I'm sure you can find rigorous proofs of this fact, but I think it's nice to see this intuitively, thinking of the derivative as the associated slope function. So a couple examples using this newfound derivative. If we want to take the derivative of cosine of 2x, this is similar to the last example where we have an inside function of 2x. So if we take the derivative of cosine, we know that we get negative sine. Our inside function is this 2x, and so that goes inside of sine, and then I have to multiply by the derivative of 2x using the chain rule. And the derivative of 2x is just 2. And so overall, when I simplify this, I end up with minus 2 sine of 2x. Now, on the other hand, let's say that we want to take the derivative of negative cosine x. Well, that negative is just a constant multiple of our function cosine x. So we get negative the derivative of cosine, and we know that the derivative of cosine is negative sine. And so here we have two negatives, which simplifies to positive. So the derivative of negative cosine x is positive sine x. Let's see another example of a derivative, and this time instead of deriving the formula graphically, I'm actually going to use what we already know. So remember that tangent is sine over cosine. And so I can use the quotient rule to find the derivative of tangent. So here, using the quotient rule, I have cosine x times the derivative of sine x minus sine x times the derivative of cosine x, all divided by the square of cosine. So, taking the derivatives in the numerator, I have cosine x times cosine x minus sine x times negative sine x. Now in the denominator, I'm going to write this cosine x squared as cosine squared x, as usual. And then simplifying the numerator, I have cosine squared x. And in the second term, I have two negatives that cancel out, and so I have plus sine squared x. The denominator is still cosine x, cosine squared x. So now in the numerator, using the Pythagorean identity, we have 1. The denominator is still cosine squared x. And remember that 1 over cosine is secant. So I have 1 over cosine x squared. Overall, we have secant squared x. So the derivative of tangent is secant squared, which seems a little bit strange, but remember this is because tangent is actually a quotient of sine and cosine. And so I use the quotient rule, and then using trigonometric identities, that simplifies. Now, I don't recommend using this method to actually find the derivative of tangent. I'm just showing this to you so that the derivative formula is a little bit less mysterious. So looking at an example, if we want the derivative of tangent of 5x, I start by taking the derivative of tangent, which is secant squared. Now, inside of the original function, we have this g of x, which is 5x, and so inside of our derivative, we also have to have the original inside function, which is 5x. And then we multiply by the derivative of 5x, which is 5. So writing this in a simplified form, we have 5 secant squared 5x. One last example where I'll derive a trigonometric formula for you. Let's take the derivative of secant. So remember, secant is 1 over cosine. And I could use the quotient rule again for this, but instead I'm going to view this as the function cosine x raised to the minus 1 power. And now instead of using the quotient rule, I can use the chain rule to take the derivative. So taking the derivative of this expression, I bring down the negative 1. My inside function is now cosine x, and subtracting 1 from the exponent, I get a negative 2. Now multiplying by the derivative of the inside of this, which is cosine, I have times a negative sine x. And again, this comes from the fact that the derivative of cosine x is negative sine x. Okay, now this simplifies quite a bit. To begin with, I can put this cosine x squared in the denominator, and then in the numerator, I have the negative and negative sine x. So the negatives cancel out, and overall, I have a sine in the top and 2 cosines in the denominator. And now you kind of have to know where you're going with this to recognize what to do. I can write 1 over one of the cosines as one part of this, and I can multiply that by sine over the other cosine. And the reason for doing this is this now simplifies as secant x tangent x, again by remembering that secant is 1 over cosine and that tangent is sine over cosine. So the derivative of secant x is secant x times tangent x. Now using this in one last example, if we are taking the derivative of secant of 7x, again we have this inside function, which is 7x. The outside function is secant, and when I take the derivative of that, what we just saw is that we get secant times tangent. Now the weird thing about this is that this function, secant times tangent, has 2 different arguments. So I have 2 different places where I have to stick my original inside function, which was 7x. And then I can multiply by the derivative of that inside function, and the derivative of 7x is just 7. So simplifying this overall, we have 7 times secant 7x times tangent of 7x. And if you prefer, you can leave the parentheses there. There's nothing wrong with it. You just might not see it there all the time. So in summary, we've found the derivatives of the first 4 trigonometric functions listed here, and you can derive the other 2 derivatives using similar methods. So the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of tangent is secant squared, the derivative of secant is secant tangent, the derivative of cotangent is negative cosecant squared, and the derivative of cosecant is negative cosecant times cotangent.